I hope you do know clouds at all now, speaking of Judy Collins, and I hope you look up, and I'm going to give you more reasons to look up, and look up at night, and look up at sunset, and look up at sunrise. There are other things to see. When you first see the sun, you're actually not seeing the sun. You're seeing an apparent reflection of the sun. It gets bent. The position is actually below the horizon. So this sun is a false sunrise. It's a delayed sunrise. And the same is true of the sunset. It's delayed. You can still see it 3 or 4 minutes after it is actually set. And what can be really spectacular, you can get a pillar, just a beam of light going high into the sky if there's kind of flat falling ice crystals. Ice crystals can be all shapes and sizes depending on the temperature of the atmosphere and its relative humidity. But of course, it's pretty cool in the morning. So if you get these ice crystals, they can light up in a sun pillar. And sometimes this pillar forms a kind of champagne glass toasting this beautiful particular morning. And this even shows up in the polar regions where you get light pillars, and every different kind of light, like sodium vapor lights and other lights, will shine up and just give you this very unbelievable effect. Almost any time of day, again, depending on what kind of clouds are in the sky, but most often at sunrise, but again, any time of day, you can get perihelia. These are sundogs, and they also are caused by, like rainbows, there are ice crystals in the air, and they're especially associated with cirrus clouds. This is a stratocirrus, or stratocumulus, and some alto cirrus. And you're looking through the edge of ice crystals, and you get this intense pillar around the sun. You get an arc around the sun, in this case, a full halo. Sometimes you see that at about 22 degrees from your vision. And these sundogs are actually a little rainbow, but you most often see the red on the inside of it. You don't see the blue. And if it is very icy throughout the atmosphere, you get this amazing combination of halos and arcs. Circumzenithal arc here, and a peri-arc here, and others that are very complicated to explain. And they're just really stunning and beautiful. Quite often they can also happen in mountains. This is a Swedish ski resort, and people got down on their knees and prayed, which is very unusual for Scandinavian people. And this is one of the most dramatic. And you can see this, not quite a full halo, but 2 different arcs, the peri-arc in here, and what is called the Circumscenital Arch. And you can tell this is ice crystals because they are producing a moderate kind of ice bow. It's not uncommon when the sun is up, if there is a middle cloud, especially a cirrostratus cloud, you can get a halo around this, and you can even get a little bit of coloring. And you can also get this from a moon, a full moon in particular, if there's high stratocirrus, which, as you recall, are ice crystals. And you can get some very eerie moon dogs. So this is actually a couple of moon dogs around this halo, around another halo. And you can see these halos are very, very dramatic. And in the past, they would call these witches' doors because they were so eerie and mesmerizing. People were outdoors more in the past, and they knew what was coming, and they'd look up, and they wouldn't always see this, but they'd certainly see it in the winter. And it really looks like the realm, entering in the realm of another world. So I mentioned moon dogs are there. You can get peri kind of arcs, and most people are just mesmerized. They don't know what it is. They often call it a pair of comets or something. Once the sun is risen, and if there's clouds on the horizon, The clouds can block the sun's rays and produce what are sometimes called crepuscular, which means morning rays. It's also called the fingers of God. And of course, photographers love to get these. It's very deceptive because these are parallel sun's rays, but because of our perspective, they look like they're all meeting at one point. But that's the same thing that happens with railroad tracks. Jesus' eyes, God's eyes, Jesus' rays, so on. Very, very symbolic of what heaven's light shining through. You can have crepuscular rays with rainbows if there's enough moisture in the air. And sometimes if there's very low stratus, you can get a dramatic sunrise and then these shadows. Of course, it was used to develop the Japanese flag, the rising sun. And there's a great many myths about Amaterasu, who was the queen of the morning, and one time she wouldn't come up, and so the sun didn't rise. And then a couple of men went out and did a striptease, and everyone started laughing, and she stuck her head out, and they got a beautiful crepuscular morning. If when you see these, you turn the opposite way and look very carefully in the sky, you might see anti-crepuscular rays. They're not rare, but they're seldom seen. They are rays that are coming in the opposite direction. Rainbows, of course, are everyone's favorite. It's a of refraction when light rays hit a raindrop, and then reflection back out. And of course, this raindrop acts like a prism, and it splits the white light into its component wavelengths. You can get another set of rain above this, and so you can get double rainbows, and you can get multiple rainbows. And sometimes, if you're in an airplane, if you're low, you might see this kind of rainbow. But if you're in the airplane and flying, the rainbow is circular, and you can usually see the shadow of the airplane in the middle of that. And you can get all sorts of combinations of rainbows. Again, this is from rain with light hitting different levels of rain. And you can see 1, 2, 3, 4. Sometimes these are reversed. So you have purple on the outside, here is purple, purple, purple. They can be inside as well. You can get rainbows from waterfalls. You can get clouds. These are very classic rainbows. Some of you may recognize that particular one, which is Yosemite Falls. Now, here we have cirrus clouds, almost cirrostratus, a little bit of mare's tail, but forming a layer. And they're high enough that when they catch the sunlight, they produce a prismatic breaking by the ice crystals. And this produces a very unusual phenomenon called iridescent clouds. They're one of my favorites, and you have to look carefully. Sometimes the sun moves pretty rapidly and the iridescence will disappear. They're also called fire bows, and they're not caused by the typical reflection and refraction. They're simply caused by bending. Where am I? I need to get my, oops. Let me get this, my laser pointer, and go back one. They're caused here by the light bending around the ice crystal, and that still splits the sky. This one you may remember as kind of a fall streak coming, and people love to claim that that's an angel. But these can be extremely beautiful and multi-layered because you have different ice crystals all in a layer, and the light diffracts around that. You can also get, at the edge of these, circumhorizontal arcs. They're mostly flat, but they can also form an arc. This is, way above the cumulus layer. This is way up in the cirrus layer. So you're looking from below up into the alto cirrus and stratocirrus and seeing this fire bow. These fire bows also form in the Peleus cap clouds on the top of big cumulonimbus thunderheads. And sometimes they get moved by wave clouds on the top and spread the ice, and it makes an unbelievable kaleidoscopic rain or fire bow. These are just beautiful. They are sometimes called Noctilucent clouds, but Noctilucent are a little different. These are not commonly seen on the west because we don't have clear access to the top of, or visual access to the top of these. So there are a lot of other phenomenon associated with sunrises. And here's a nice squall line. And here's lightning. And lightning is a natural electrostatic discharge. We're always fascinated, but California is very limited in how many lightning storms it gets a year unless you get up into the Sierra Nevada. It's rare that we have lightning simply because we don't have the instability of most of the frontal rains that come in. When they have to travel orographically over the mountains, that creates a thickening of the cumulus nimbus and also an instability in charges on the clouds. The charge comes from updrafts, and you get a positive charge up high, you get a negative charge down low, and then the Earth is positive. And since charges go from one to the other, you typically get a lightning from a negative charge to a positive charge. And sometimes the charge will start in the ground as well and meet going up. These lightning strikes are incredibly fast. They travel at the speed of light, essentially. There may be 40,000, 44,000 during an average day. And they strike the Earth, depending where they are, up to 100 times a second. They're incredibly powerful. The temperature in those bolts goes up to 50,000 degrees centigrade. Of course, that heats the lightning or heats the air, and the air has to collapse, and that collapse is what we know as thunder. There are a number of types of lightning, and some of you who've lived elsewhere have seen lightning, in particular what we call cloud to cloud. There's cloud to air. That's not that common. Cloud to cloud, our inner cloud, this is within a cloud, you can have cloud to cloud. Within the cloud is about 2/3 of all lightning. So lightning that's generated within the cloud from an area of negative to positive charge. And then about another 1/3 of all the lightning is what we would call cloud to ground. And as I mentioned many times, there is a charge that comes up and meets the charge from the cloud or the bolt from the cloud. Sometimes these charges are so hot that they actually ionize the oxygen in the air. And when you get that, you basically ionize the oxygen and it gives off its typical spectrum, its electromagnetic spectrum, which is green. Here you can see a cloud to cloud. Here you can see cloud to air. And here you can see a major bolt, but with tendrils going all over the place. And this is also a mix where it is intercloud, cloud to cloud. So even in one quote unquote strike, you can get everything happening at once. There can be odd shapes, reconnections. Love to see these, that someone makes them into a heart, but I've never seen a heart in the lightning, although my heart has been shocked enough times. Where do we see these? Tropical regions, where the air is rising. The air at the equator is heated, it's moist, it rises, it cools off at the tropopause, and it then begins to spread poleward. And in the United States, this mostly occurs in the Southeast and of course in Florida. I've been east now for 2.5 weeks and had about 5 thunderstorms plus 1 tornado. There are other places that generate their own phenomenon. This is over Lake Maracaibo in Venezuela. this is a time lapse, so don't think you'll ever see this, but this is a, you just leave the shutter open for a long time and you can get this. It has about 160 nights a year with lightning. Then the storms last over 10 hours and there can be almost 300 strikes per hour. Now, recently with the space station and also satellites being set up into these and drones, we've now discovered that the lightning can split apart protons and actually make X-rays that are descended. It can also split apart nitrogen and oxygen and carbon and create very rare short-lived radioisotopes. So just a quick primer about the electromagnetic spectrum. There's only a very short section that produces visible light. The longer wavelengths are microwave and radio waves with different frequencies, AM and FM. And then these are ionized. So you can get X-ray and also gamma radiation. And this is pertinent because the Firefly, which was launched in 2013, along with the space station, has discovered that when there's tremendous lightning storms, so this is the top, actually, this is something called an ELF, but this is looking down on a lightning storm from the top. You're flying and this is from the space station. This is what we call Earth glow. This is at night, but the atmosphere still glows, mostly from sodium and oxygen in it. But this satellite has detected when there's lightning below these big, huge cumulonimbus, there are pulses, bursts of positrons and electrons and gamma rays released. And they're very, very short-lived. And the positron and electrons annihilate each other and release these gamma rays. So here is the space station looking down on the top of one of these. And we now know that there are pulses that follow a magnetic line from the Earth, huge gamma ray pulses, but they're very, very short-lived, 0.2 of a second. And they're charged by these positrons and electrons. And it turns out that most of these occur over the ocean, and they can occur with any kind of storm. So this is now recording all the time. There are 2 more satellites recording these. And now this is, let's see if I can get this. Look at this. This is the top of a thunderstorm. And this is how it's recorded. This is a gamma ray burst. Come on, let's see if we can get it again. There's a gamma ray burst. And then it ionizes the very top of the troposphere. And it creates what we call an ELF. And then it goes off. And these particles destroy each other. And these are too quick for cameras, but these are electronic instruments on these machines that record these. However, people have photographed the ELF, and these ELVs are short-lived because they spread out and dissipate very, very quickly. Now the ELF, I love this term, transient luminous events. It sounds like a pickup line to me. Would you like to see some transient luminous events? They are large-scale optical events. They were first quantified in 1990, and there have been dedicated programs to see these. We mentioned the ELF. This is from an electron gamma ray burst. And quite often when the burst occurs, that burst may ionize nitrogen. And when you activate nitrogen or ionize it, you get a red absorption spectrum. And then you also can get a blue one. So this is called the sprite. And you can get some other things coming off the top of these enormous thunderheads. Some have been named, but not really understood. So there's pixies and gnomes. These used to be called gnomes as well. blue jets. The blue jets can be little starters, they can be enormous, they can be gigantic, and they can have huge sprite explosions. And they can shoot up about 35, 50 miles. They can go higher than the ionosphere. So here's a beautiful picture from this space station of an actual blue jet coming out of the top of a thunderstorm. And these can then produce sprites, as you see here. And this one obviously has the blue from nitrogen that's not so ionized and a little bit of red from the rest of it. So here are a collection, and these are only very, very recently has anyone even been able to develop a light motion activated or light activated lenses that are fast enough. And if you're far enough away from the thunderstorm, you can actually photograph these things. So there are gigantic jets, small jets. You can get bolts from the blue. That's just lightning going from cloud to air. And you can get spiders that are going to the air or going down and so on. And there's zigzag ribbon, which means the lightning bolt goes back and forth. And there's even ball lightning, which I'll talk about. Red sprites are just glorious. They last more than a second or less than 2 seconds, 3 seconds. They're mostly red. They can do all kinds of shapes, plumes, columns. My favorite is the jellyfish. I think there's a jellyfish up here. I can't see that. And this again is shot from the space station. These were not known until they were photographed from space. And you can see the sheet lightning in here in this big thunderhead, and then this sprite on top of it. And this is the what is called the Earth's green halo. What happens with these sprites, there's a thunderstorm down here, there's probably a huge bolt of lightning going this way, but lightning discharges out of the clouds because there's another negative discharge and then another positive discharge out in the atmosphere. So the top of this cloud may be negative, positive, negative again, and then there's another discharge. And this discharge is so intense, it heats up and ionizes the nitrogen. And when nitrogen is ionized, it glows red. And we'll see this, by the way, with solar photons that will light up the upper atmosphere in the same way. But if it's continuous and it pulses and forms ribbons, then we call it an aurora. But these are generated by the clouds, and they're very, very short-lived, whereas the auroras are generated by solar storms coming into our planet's magnetic field. So beautiful, short-lived, seldom seen unless you're up in space, but now there's a movement, people going out, especially in the Midwest, to photograph the top of thunderstorms. This again is one of the shots from the space station. You may also, once you get this sprite, a gamma burst, you may get an ELF, an emission of light and VLF perturbations due to electromagnetic pulse sources, hence ELFs. I think somebody was reading Tolkien and decided on sprites and elves and gnomes and so on, and pixies, which no one has completely identified yet. But these can be visible either as kind of pale with a little bit of sprite seen in it, or just these reddish halos that are very short-lived. They spread rapidly and then disappear. So all the way up to basically 50 miles or so, you get these elves, blue jets down here, and huge and enormous, elaborate sprites. Now, if you ionize or heat up nitrogen gas, it's going to emit light, and it emits light in 2 wavelengths, generally a very long wavelength and very short. So you get reds and blues or purples. So this is the absorptive spectra and also what is released from diatomic nitrogen. So you get red and kind of blue and purple. So when you look over here, this is the whole outer stratosphere that is ionized, and you get nitrogen glowing red up here and nitrogen glowing down here as purple. And as you go up, the nitrogen level increases and increases rapidly. Remember, it's only about 80% nitrogen at the surface, 21% oxygen close here. But this is where the sprite occurs because it's also one of the increasing zones of nitrogen. And then oxygen drastically, monatomic oxygen decreases and diatomic oxygen increases. And then right about here, you have a layer of triatomic oxygen, which is known as ozone. So complicated things, and very recently, some photographers were able to catch this phenomenon of glowing green at the top of sprites, and that is actually the spectra emissions of oxygen. So you're getting nitrogen and oxygen. And these colors are also the colors, because of oxygen and nitrogen, of the Aurora Borealis. Now you can get all of these coming together. So this is a huge thunderstorm down here. There's probably still a thunderstorm off in here. You see how the anvil is up there right at the tropopause. So this is the stratosphere. You got a very high alto cirrus, our Cirrus Clouds up here. And here you have a sprite. And this glow is probably partly due to an aurora event. Now, there's a lot of moisture up there, and moisture, this is all convected back and forth. And how this moisture falls, it will almost, if there's a big enough cumulus cloud, it will turn into snow or ice. But if it falls through warm air, it will melt. If it falls through cold air, it will freeze. If it falls, it may freeze into sleet if it hits cold air when it comes down. And sometimes if it rains and then comes down into extremely cold air, you can get an ice storm. And then of course, if it's uniformly cold all the way down like this, you'll get snow. And snow is one of my favorite substances on the planet. I've taught many courses, believe it or not. Sorry, Brian, on snow. I used to be a snow and avalanche expert and taught numerous courses for Department of Water and Highway Department and others who are interested in avalanche safety and skiing. But something you people will never see is, unless you grew up back here somewhere, if you get a rainstorm, a warm rain coming in and it's rising over cold air, you may get snow way out here because it's falling through cold air. You may get sleet, but if it's falling really basically from snow to melt to ice, then you get these ice storms. And they most often happen when you get a low pressure coming up like this. The circulation around the low pressure is like this. The circulation around the high pressure is like this. So it's bringing down extremely cold air. This is rising over the cold air. And so you get ice storms. And they can be very problematic. And you see what happens to power lines. I remember playing ice hockey just on the street, just down my block, and then skating the next day to school. But it turned out it was closed. If you have a very complex thunder supercell, then the snow may come down, melt, but get caught in an updraft, taken back up and refrozen. And then because it gets heavier, taken down by a downdraft, taken up again, refrozen. And this can happen cycle after cycle after cycle. And this produces hail. And hail balls can be enormous. They're often very distinctive in terms of their anatomy and also their size. Their anatomy is such you can see how many times it was taken up, frozen, refrozen, melted, and so on. You can cut these in half and see, and sometimes you can see it when it falls. Of course, the real tragedy is if you are out with your car or an airplane, what's going to happen? And these hailstones can go right through. Tragically, I had to assist a woman whose child died by being hit by a hailstorm when she was making a dash to a grocery store. And I don't know why she did that, but anyone who's around these events usually knows you don't go out in this unless you have a helmet on. Snow is frozen H2O, and H2O is a very curious molecule. Looks like Mickey Mouse with one nose. They have a positive side and a negative side, and they tend to bind positive to negative, and they tend to form these hexagonal loops. And this is part of the nature of how they form initially around a nucleating disk or a nucleating particle, just like rain does. Sometimes airplanes will spray iodine particles, crystals, to aid the nucleation of snow. Initially, you get this hexagonal plate. Later, it grows a little bit. You get more hexagonal plates. This is an electron stereoscopic view of what can happen. There's the original hexagonal plate with riming. And if you look closely, there's actually needles and other sorts of things. The function of the type of ice you get is a matter of how cold it is, from 0 degrees down to -30, and also the relative humidity. And so you can predict what is going on in the cloud by seeing what kind of snow crystal falls. Very few people have ever seen needles because these needles tend to be extremely cold. They will form in the upper atmosphere, but then they're usually lost. So this was developed by Japanese scientists. You can actually use this to predict what kind of snow will fall. There are many types of snowfalls. I actually have about 100 different terms for snow. Eskimos don't. Snow researchers do. It's a myth from anthropology. They have more terms for ice, Inupiaq and Inuit, than they do for snow, because ice is more crucial to them. I would love to talk at length about snow, but I'll have to just leave it with Hokkaido, which along with Shasta and Mount Lassen are one of the heaviest snowpacks in the world. Lassen at some times has had over 50 feet of snow. California gets tremendous amounts of snow, believe it or not. Hokkaido, because of where it's based in northern Japan, gets over 60 feet of snowpack. This is the bus ride up to the main ski resort, and that's over 60 feet. And you get these wonderful, what are called, in Inupiaq call it kali snow. This is called wet snow, and it sticks to everything, forms these wonderful mountains and monsters. Now, in hot regions, air is often bent because you may have cool air and then heated air, and that heated air rises on a thermal, and light may be bent. The light waves may be bent back toward where you're looking, and so what you see is something remarkably weird. That is a superior mirage. You look at something that's not there, the bend wavelengths lift the image out of the horizon. So you can have something floating, a car floating, mountains floating, and so on. This is a classic superior mirage. You can also get this happening in relatively cold air, but still if it's warmer down or cold, really cold down below and a little bit warmer up above, you get the same bending of light. In this case, it can lift up icebergs or ice shelves, and you can even get a mirage, an upside down mirage of this iceberg or ice cliffs. You can get land. This is in the Suez. This is in east of Svalbard. And this is a cruise ship, and you often see them upside down, or this is a very classic Norwegian training ship that looks like it's just floating on air. This is probably where the origin of the Flying Dutchman come from. This is called a Fata Morgana. And there's lots and lots of legends about the Fata Morgana and what you actually see. This is a city silhouette that's lifted. This again is mountains that are lifted, ice caps, an ice cap, and these are cargo container carrier ships that are inverted. All right, let's go. I just throw a couple of these things in. If you're sailing in the north and you suddenly see an opening in the clouds, that probably is not an opening per se, but a reflection of ice, floating ice. So this is called an ice blink. Here you have a really massive tabular iceberg, and the sun gets through enough to reflect back into an ice blink. And so that tells you, don't sail that way because there is an iceberg near it, and there's an ice blink again. Some of you read adventure stories and you might encounter this ice blink. One of my favorite phenomenons, and one I hope you get to try sometime, it gets its name from the Brocken Mountain in Germany. And early climbers realized when you're on top of this mountain, and if the sun was behind you and there was fog sort of in front of you and you cast your shadow, the shadow would extend for great distances, miles even, but you would diffract the light enough to produce a rainbow around you. So here you can see actually two rainbows, but you look sometimes fantastical. We used to hold our ski poles and make incredible creatures like this. It's easy to do. You just have to get up on top of the mountain. There are many, many stories. Again, the sun setting below you is a great time, and on the opposite side, cast this shadow. It's called the anti-solar point, but you can see a bit of a rainbow, two rainbows in this case, and they can go a great distance out from where you're standing. And of course, you can produce the effect that you're a god or a monster. And of course, over time, these figures have given rise to stories of like the thin, the black, or other kinds of mountain monsters and so on. And you don't really need to be on top of a mountain. If there's dew on the ground and the sun is rising behind you, you face the dew, and the dew will reflect the bent light around your head into a glory. So here is what happens in a broken mountain shadow effect. This is called the glory, but many times the glory when you're down low won't show much of a rainbow. Here there is a rainbow, but down here there isn't. And you don't have to be really high to cast this. So this is probably one of the reasons that we get so many stories about what is called Heiligenschein, which is the German for halo, and why we often picture saints and others enshrined in some sort of halo. Another one of my favorite phenomenon, just because I love being in these places to see them, is the sunset. It lingers at altitudes. And not only does it linger because of the descending sun, your descending sun is actually still below the horizon, but it will show wavelengths that will get through the atmosphere in the red wavelengths and then backscatter off the mountains and so on, creating this pink smoldering or alpenglow, as it's called, or Alpengluchen, the glowing mountains. And you can get a different kind of alpenglow if there's mist below this. You can get the mountain in the background lighting. from the sun's rays being bent down there, and it lights up as yellow, but quite often you get this alpenglow. And especially in the Sierra Nevada, this may be familiar to you. A couple of these places are, this is the Owens River. The Sierra Nevada, with its incredible granites, is called the range of light because it often gets, it's so high that it often picks up alpenglow. In Alaska, everything is really high and you begin to see alpenglow. Also, if you're careful, you will see sort of a dark purple line and then the pink line up here, then it kind of gets a smudgy yellow. I'll tell you about that in a minute. But we should talk about why the sky is blue. Well, the sky is filled with all kinds of gases and all kinds of little particles, aerosols. And when the sun's light hits this, the shortest wavelengths, the blue and the ultraviolet, tend to hit these. Its wavelength tends to be the type that it will interfere with particles and scatter. And this is called Tyndall or Rayleigh blue scattering. The longer wavelengths of light will keep coming through. And that's why we see the sun as red and yellowish. But the blue is scattered back. So that's what we see when we look at the sky. It's blue from this backscattering. Now, we mentioned about delayed sunset. Well, there are three measures that are kind of important for business and shipping and sailing and other things in astronomy. When the sun is just about almost to the horizon or past the horizon, and you'll still see it up here, that's called the Civil Twilight. If it's about 6 to 12 degrees below the horizon, it's called Nautical Twilight. And if it's way below, then it's going to be dark, and that's called Astronomical Twilight. It's interesting, if you reverse this, you'll find that some birds will sing in nautical twilight and some birds will start singing in civil twilight. I wake up every morning to this incredible mockingbird who just wakes up about 5 o'clock and starts singing around the house. And again, at sunset, you can get these anti-crepuscular rays. You just have to turn around and look back where the sun is actually rising or would rise. And again, these are parallel, but because of our perspective, they look anti-parallel. This is taken in Thailand. And why does it light up? Well, and this, I like it because not only is that yours truly, this is an anti-sunset because this is looking west up Carmel Valley. So this is the sunset opposite of where the sun is setting. So if you're looking at the sun going down, the long wavelengths of light will reach your eyes. Everything else will be bent. So most of the atmosphere will turn reddish to yellow. And especially if there's more stuff in it, like dust, atmospheric disturbances, smoke, particles, as you may have noticed last summer, tremendous sunsets. And this is a true sunset. This is Carmel Beach. You can get intensely red sunsets if you get a lot of dust. This is one that was Mount Pinatubo from Utah. And sometimes when the sun is going down, you sort of get a reverse pillar, but it's over the sun where you most are over an ocean or a river where you see this. It's not a sin street. Trust me, it's a sun street. You don't want to look in there. Now, if you follow the sunset, you get sometimes with different layers of different temperature air, the sun can spread. This is a time lapse. The sun is setting and each of these shots represents a different stage. You can sort of see blurs in here. And I want to show you one of the most unusual phenomena. It can happen at any stage, but it most often happens right when the sun is going below the horizon. At this stage, it's actually a disappearing sun. The sun is below the horizon, and it looks reddish and yellow because the long wavelengths of light are bent back. Now, if there's moist air above this, or at least some unusual air, then the short wavelengths of light will be bent back as well. So the blue and the ultraviolet are not usually bent back because they're so short, but the green is. And so this is being bent back over the false image, and you get this very, very short-lived green flash, a rayon vert. You can get it. I've actually seen 14 of these at one time when the sun, if there's different atmospheric layering, you can get a green flash, green flash, green flash, green flash. This was thought to be the sun shining through the ocean. It wasn't demonstrated until Kodachrome came along, and the film was sensitive enough to the shorter wavelengths of light it could pick up the green. And the first time it was photographed by the Vatican Observatory. They have a very nice telescope and outside of Rome. This is spectacular to see this. It's best to use binoculars, but don't look at the sun when it's like this. Look at it when it's just about gone, and you will see sometimes an enormous kind of green flash. It just lasts for a second at most. Don't look directly into this, but it helps to either use a telephoto lens or a very good pair of binoculars. And it also helps. Margaritas will do this too. I would tell my friends at sea, if we didn't see this, that they could go down to their toilets and turn off the lights and wait for a minute and then flush the toilet. And they would see a green flash or green flush, which means that the water that they flush their toilet with is actually seawater. And if there's phytoplankton in there, the agitation of the flush will turn them into green or blue flashes. So you can get a layering, different layers, and you can get green flash after green flash. Here you can see them stacked up. Most of these, by the way, are taken with supreme telephoto lenses. And if you're exceptionally lucky, and this is a friend of mine, Rhonda Valley, who is a whale scientist, and I worked with him many, many cruises. And this was in Alaska, which is surprising. You can get this rare blue or purple flash. This means that there was some reason that the blue light was bent back strongly enough that you could see it. Normally you could only see the green light, but the blue wavelengths, which are shorter, were bent back. Now, I mentioned when you watch, say, a moonrise or a sunset, you actually can see the Earth shadow rising. Now, this is a little bit hard to understand, but when you think that you're at the horizon and night is coming up around the Earth's surface, night doesn't fall, it rises. And when it rises, you can see the shadow itself. And then you see this pinkish from the long wavelengths of anti-crepuscular long wavelengths of light, and it's sort of an alpenglow off the atmosphere, and it's coming back to your eyes. And that's called, that pinkish backscatter is the belt of Venus. And here you can see it really, really well. This is the Earth's shadow rising. Here's the belt of Venus. Belt of Venus, Earth's shadow coming up. This is Shasta and Shastina. And you can see how there is that backscatter from the long wavelengths of light coming like this. And you have to run pretty fast to keep seeing this because eventually it will disappear and you're out of luck until the next sunset. This is Comet Lovejoy from 2015. Really nice shot from the space station. This is the night shadow, the Earth's shadow. This is the belt of Venus, and this is what is called Earth glow or air glow, and it's yellowish green. You can sometimes get the shadow or the belt of Venus reflected. It's a wildlife refuge in Colorado. Some of you may know this as Mono Lake. And again, here at Zion, or excuse me, Bryce, you can see the shadow of the Earth really well defined, and just a little bit of Venus's belt coming up. There's some lenticular clouds forming. You get a bit of an aspen glow up here too. This still is the Earth's shadow. It doesn't look as dark as it should be. And this is taken on the White Mountains looking east. Or sorry, looking west. Sierra Nevada is over here. And again, if you turn, you can see these anti-crepuscular rays. And these are quite often just shadows cast by the clouds. Here's the Grand Tetons. Each of the Tetons is casting a shadow up. Again, sorry, I guess I duplicated this. This is in Thailand. Now, one thing you need to kind of practice looking for, and this is Zodiacal Light. And it happens right at sunset. Once you can still see the belt of Venus. And if you look toward the rotational ecliptic arch, this is going to look back toward the sun, although the sun is already set, that's a false sun. And you're going to see reflected off all of this basically solar dust, dust from the primitive planetary system of sun and earth. This is a reflection on the zodiacal eclipse. It's not the Milky Way, which is the edge of our galaxy. This is the edge of our solar system. And it will be a bright spot, and it varies according to the time of year, whether it's in, the Pleiades or up at Cassiopeia. And so in essence, you're looking back from the Earth into the sun's ecliptic and into the dust. This is also called Gegenschein, that is the countershine of this dust. So we do have another asteroid belt and Kuiper's belt and so on, and comets, but right in the inside is this dust left over from the formation of our solar system. These are planetesimals out here in the asteroid belt. But so if we're looking from Earth back toward the sun, we will see this dust. And it will shine and be very bright. It doesn't have anything to do with the Milky Way. And it is called the counterglow from the solar dust. So here is the arch of the Milky Way, and here is the zodiacal light. Now this is night. And night traveling, this is what you'd see from the space station. Night traveling back, and if you were down here, you would see the Earth's shadow rising in the horizon. And you can see, you don't see the Earth glow as much because you still see sunlight in the upper atmosphere. Now, two cloud types, which I haven't talked about. And I'm going to talk about them because they're really atmospheric phenomenon other than clouds. And the first one is actually fairly low. They're about 20 miles up. They're in the stratosphere, above where clouds normally form. Remember, the troposphere and the layer between the two, the tropopause, is where most of clouds and weather occurs. That's about the level where jet liners will fly. But in this stratosphere, there can be clouds that form basically from nitrogen and from meteoric dust. And not everyone is sure that this has probably been around for a long time. Nobody's sure if people have seen it in the past, but it's certainly been photographed a lot recently. The other cloud is 50 miles up, out of essentially our atmosphere, because when you're at 60 miles, NASA basically considers that the end of the atmosphere. And from here on, the temperature just gets colder and colder and colder. This is the area where auroras occur, but meteors hit this level in the mesosphere and they burn up, and the dust filters down and they get caught in very peculiar ice. And I'll talk about these polar mesospheric clouds in a minute once we talk about the polar stratospheric. You can see the two examples. These high ones are called Noctilucent. They have multiple names, but you can remember them. It's one being in the mesosphere and the other in the stratosphere. So this is what we're talking about, atmospheric dust from meteorites. Whenever you see a meteorite, and this is burning up, it's going to turn into, this probably will not land. It's probably been incinerated. So this is simply called a meteor. If it lands on Earth, or well, it depends. If it goes into our atmosphere, we'll call it a meteorite. Rarely does anything fall. It stays up in that upper atmosphere, but it can produce a major dust trail. And here you can see the dust trail even at night. This is a big burst of an enormous meteorite that was broken up, actually an asteroid that was broken up and measured. Its dust was one of the first times it was measured. So polar stratospheric clouds, also known as Nacaris clouds. And nacre is the fancy term for mother of pearl. And it's, in essence, an iridescent produced by layering, in this case, of ice crystals and the diffraction of light waves around these ice crystals. It also, these ice crystals are not, they're more nitric acid with water associated with them, and it's called nitric trihydrate. They're hydrated nitric acid. So this serves as a nucleation molecule for other molecules of water vapor. So this is ice, nitric acid ice, with water vapor frozen on it. And this produces nacreous clouds, pearlescent clouds. And these are among the most spectacular clouds of all. This is another asteroid that's burned up, a small one. But these clouds, these stratospheric clouds, are mostly from different ablation from the meteorite and fragments, and also the particles of magnesium and iron that are in these, along with the nitric acid in the cloud itself. They're phenomenal. You can see them. Even though they're 50 miles up, that's not very far. You can see these things. Unfortunately, we worry a little bit about the fact that all of this nitric acid can interfere, and chlorine can interfere with chlorine molecules and strip the oxygen off of them and thereby destroy ozone. This is a big concern today, and nobody knows whether this is a recent phenomenon or if it's been an ongoing phenomenon. We've launched a couple of satellites, but nonetheless, it is still spectacular when these occur. They also occur in polar regions more than any other region, but they can be seen at almost every latitude. This is actually an ice motel in northern Norway. You sleep on caribou skins, but the bed is made of ice. It used to be a water bed, but it froze. So nacreous clouds, unbelievable. Then we get these even higher clouds, 50 miles up. You can see above, this is almost what NASA considers the end of the atmosphere. They're mesophilic clouds, or mesophoric clouds, and they're also called noctilucent or night glowing. And they do tend to occur around the polar regions in the polar winter. So they can occur around Antarctica also in its polar winter. They are seen, however, elsewhere. So here's the Nacaris clouds down here. Here's the Noctilucent Clouds. This is the air glow. I'll talk about this again. And this is where auroras occur, and this is where meteorites would hit. So Noctilucent clouds are way up 40, 48, 50 miles or up to, well, 90 kilometers. And they're very eerie. They just look like the sky is glowing in this noctilucence, which means night light. It does look like ocean phosphorescence, which is another name that's usually applied, atmospheric phosphorescence, but it doesn't have anything to do with phosphor. It has to do with ice. And they're very, very beautiful. So here we are. There's the atmosphere of Earth. That's how thick it is. You're just seeing it disappear into the shadow of night as the Earth is turning this way underneath the shadow of night. More things to think about. Remember when you're traveling to look up and see these, especially sunsets. People at Santa Cruz every night go out to Lighthouse Point and line the area there to just watch the sunset, especially in the summer months. It's a real treat to see, have clear air to watch sunsets or sunrises. There are a few books, there are not a lot on sky phenomenon. I've listed these in your bibliography. But what I'm going to talk about next time, of course, is the aurora. And here you can see, again, a little bit of air glow, earth glow. It should be a little more green, but this is an aurora up above the mesosphere, basically traveling all the way across the northern hemisphere. And it's dependent on ionization of our upper atmosphere, nitrogen and oxygen primarily, from solar storms. And this is tied to solar spots, sunspots, which are on a 12 to 14-year cycle. And we're just increasing. We're just heading toward the peak of that cycle in another 2 or 3 years. So a good time to travel. You can go online. I'll tell you where to look. And sometimes if the solar storm is really powerful, it can bring these things way down. I've seen them in Santa Cruz. I've seen them actually in Europe. So it's possible to see them in lower latitudes, depending on the solar activity. And then along with auroras, I'm going to talk about meteorites and firefalls and things like that. These are two recent ones. This one was seen in February, and it actually did have a firefall. That means this burned up. Enough people watched this, enough security cameras caught this, and all over the United Kingdom, they were able to reference this and figure out where the fall would have occurred. And so immediately people began to go out there and pick up all kinds of pieces of meteorite. That happens very rarely. Theirs is a tremendous meteorite that burned up over Belém. And then this is a great fireball with another very quick one behind it.